Hello, everyone. My name is Yishai Galatzer. I'm from Amazon Web Services, and I'm the manager of the Corretto team. Today, I wanted to talk about how we migrated the Lambda's front end from Java 8 to Java 11. I want to be specific. We're talking about the services behind Lambda and not your actual code running on Lambda. So my team builds Amazon Corretto, which is a downstream distribution of OpenJDK. Last year, we had the honor here in the keynote to launch Corretto. And we promised a few things, which I just want to report on. Last year, we launched Java 8 as a preview. And since then, we added GA releases for Windows, multiple distributions of Linux, Mac OS, and ARM64. We also promised to grow our contribution to the open source project, and the Corretto team, along with Red Hat and SAP and Oracle, are the maintainers now of OpenJDK 8U and 11U. So if you're using OpenJDK, we're happy to provide that service to the community. In July, we also launched another major feature. It's the Amazon Corretto crypto provider. This is a component shipping in Maven Central that improves CPU performance quite significantly for encryption. So your modern services today are encrypting at rest, using TLS, signing payloads. We've been running this again for about 2 years in Amazon. And since July, it's now available in the public. It works with every JDK distributions, including Oracle's and Red Hat's and ours. And all you have to do is install the provider, install the Maven package, and pass the property files. And we'll be glad to see you using it. First, a little bit about Lambda, so you can understand the scale of what we're doing here. AWS Lambda is a compute service that lets you run code without provisioning or managing servers. Lambda today processes trillions of requests across hundreds of thousands of active customers every month. It is available on all AWS regions, and customers use AWS Lambda to build highly available services. So it's quite significant for us to go and make these deep changes in Lambda. Let me jump a little bit into the architecture of Lambda. So the customer on the left side is starting a request. That request is going to eat an application load balancer. That load balancer is going to go into the front end, which is the service we're going to focus on today. The front end basically takes your request and does a few interesting things. First, it authenticates you and makes sure you have the permission to run this code, right? You don't want other people to be able to run your code and do stuff with your data. It then talks to a worker manager, and the worker manager's job is to find a worker. That is where your actual code is going to run. If it needs to warm it up, it warms it up. But in this case, what we're going to focus on today, you're going to focus on the synchronous case. So your request came in, there is a worker, it has your code already, and you want to invoke that Lambda function. The service is written in Java, and at this moment, we're going back a few months, this code is running Corretto 8 and ACCP. And the point of this code, because it runs synchronously, every millisecond spent in the front end is additive to the time your Lambda function runs. So we obviously want to get this latency down as much as we can. So let's start measuring. Unfortunately, I cannot share the exact numbers of the actual latency, but this is a pattern that we use across all our services when we measure. So what we do is we measure the latency, and we look at it across multiple percentiles. In this case, I'm going to look at the P50, which would be the median, P99, P99.9, and then 4 nines. Even at 4 nines, we're talking about one request out of 10,000 requests. And when you talk about trillions of operations a month, we're talking about many billions of operations that's going to run at that at these numbers. So we advocate please, when you measure latency, don't just look at your P50. Look at your P99.99. In some cases, you might want to look at your P100 and figure out where you stand. So obviously, at this point, we want to bring this number down. And we're moving on. We're going to keep measuring and figure out what's happening. So what is the most common thing when you look at a Java application that runs a little bit slower than you expect? You look at one or two things. You look at your dependencies. You look at things like I/O, which will also be a dependency, and you look at garbage collection. So let's look at our garbage collection pauses. Again, when we look at a garbage collection, we also want to measure it at multiple latencies. So here, though, the percentiles are not the same as the percentiles in the previous graph. Garbage collection pauses don't happen on every request. They happen once in a while. So when we look at them, and we look at P1, P1 would be the bottom 1% of all pauses, or kind of the floor. The floor would be a 50 millisecond pause, and 4 nines will be 140 and something millisecond pause. Again, these percentiles don't match one-to-one with the percentage on the previous slides, and you want to keep that in mind as we keep going forward. But obviously, the numbers are slightly high. They're not terrible. We want to see what we can do about them. One very common thing when we look in Amazon at when our latencies go up, we look at this metric called heap memory after GC. What is this metric? We basically look at the memory after a mixed collection has run, and we record that number. If you look at percentiles here, again, they're different. There are percentiles of the servers. We have a lot of servers running this service, and P100 would be the server with the highest heap use. So we look at 23%. In this case, this is a very good number. When we go to 70, 75%, we start getting worried. At 20%, it means you have quite a lot of headroom. Now, if you want to ask how you're going to do it yourself, we just put out a pull request in the Corretto repo, pull request 177, that shows how to go about collecting that data and reporting it as a metric. I'm not going to go into the detail here, but feel free to jump here and take a look. So continuing, the next thing we want to do is we want to measure the allocation rate of the application. So one of the first things we do, it's something I would go back home if you're not doing today, turn it on your service. Start capturing GC logs. Almost every single time when a customer comes to us and asks for help, we say, hey, can you get us the GC log? And too many times they don't have it. So these are some really good flags to use. You want to print the GC details, save it to a file. You want to rotate these files. So you want to make sure that if one file got corrupted, something happened on that machine, you have the other files available. And because you rotate the files and you limit the file size, you're in a good place. You're never going to run out of disk space, right? We don't want to create outages by trying to measure them. So keep that in mind. And let's look at the content. So we're using, in this case, the G1 collector. And it's a file with a lot of details, so I highlighted the two interesting details. At 5:18, we evicted 11.7 gigabytes from Eden. About 5 minutes later, we did it again with very few survivors. It's like 0.1 gigabytes of survivor. So the math here is quite trivial. 11.7 divided by 5.5 seconds, 2.1 gigabyte per second. That's a, I would say, high number. It's not terrible. I've seen applications run with 7 and 8 and survive. But this is not a tiny number, and we're starting to get suspicious here. But as we want to measure, we also want to have a metric that is not load dependent. So a lot of these services have these patterns, right? During the morning, you might get a spike. If you're doing order or food delivery, you get a spike during lunchtime, right? So this memory allocation per application is highly dependent on your load. We want a metric that actually looks at the app itself. So we introduced this metric called measuring allocation rate per request. Here's a sample way to do it. This doesn't work with continuations. It works with the older model of if you run on a single thread. Obviously, we also have solutions that can do it with continuations. It's just a little more complicated to show here. But the idea, again, we create something called an allocation stopwatch. We go get the thread MX bean. We capture the thread allocated byte. And when at the end of the request, we capture 8 again, do one minus the other, and we have our allocation rate per request. So we deployed that. What we noticed quickly that is actually quite expensive. What happens when you call get thread allocated bytes and you had 5 threads, it's okay. What it does, it allocates an array with 5 values. If you have 1,000 threads or 2,000 threads, it allocates a lot more, and it's starting to become quite heavy. Like I said, we don't want our metrics to influence the application. So in this case, and at this point, what we did is we went to a sampling mode, and we sampled a small percent of the threads. But we also did a fix. So we have a fix proposed to OpenJDK that's going to make this a lot more efficient, where we can do 100% sampling. This is pull request 170 on Corredo, which we're going to contribute to OpenJDK. So what you get here is a very nice flat line. Let's just remember these numbers. Our highest request, again, we're looking at percentiles. Our P99 request allocates a little over 3 megabytes, and our lowest request around 500 kilobytes. I really recommend with this to do 2 things. One is you want to put alarms. So if all of a sudden your allocation rate per request popped up on your next deployment, you can catch regressions before they hit a problem when traffic goes up. You might deploy at a low time during the day, and then later during the day, let's say you didn't run a load test or your load test didn't catch everything. Later during the day or later during the week, you might be wiped out. You also want to look at that long term, over a period of weeks and months, and you can see regressions in your application. So what are we doing now? We got to a point where we can go and make some improvements in the code, or we can go a little bit brave and look at JDK 11. So JDK 11, a lot of the features in JDK 11 came in JDK 9, actually. That was released in September 2017. But JDK 11 introduced this amazing feature called long-term support, which means we can actually take our app and put it and have, if you recall, until 2024 to run this app without having to worry about constantly upgrading it. So you have all these great features, and there are quite a few good talks today about all the new features in 9, 10, 11, 12, 13. And you heard a lot of good stuff about them, and I'm just going to ignore them, because I want to talk about these 2. In JDK 11, the garbage collection, G1, became the default, considered no longer a, I don't want to call it experimental, but it's a feature you can use in production. The full GC has been parallelized. The object copy phase has been improved. And my favorite feature, actually, are compact strings. So it turns out that a lot of your apps are allocating strings. What a surprise. And it also turns out that most of these strings are English or Latin 1 strings. So what happens? Let's look at the example. It's the string Amazon. This will be in Java 8. And we have a lot of zeros in there. If you go to Java 11, you don't have to change your code. It's going to be represented with this extra byte called coder that tells Java this is a Latin 1 code page, and the string is about half in size. The bigger the string, the more efficient you are. So we're quite excited about that. But before going to 11, the team still felt kind of anxious about a big change. And they went and tried this flag, use string deduplication, run it, and they found their heap size got reduced tremendously, almost 80%. They're super excited, try to run it in a load test. But what actually happened is while your memory consumption went down, the GC pause time are increasing. But this was a strong encouragement to go to JDK 11. And what I would recommend, if you're running a JDK 8 app and you're not yet you don't think you need to go to 11 yet, turn this flag on, measure your memory. If you see a large reduction in memory and your app is, you're running a service, you're serving requests, I would say don't use it. Put it down. You have a really good reason to go to JDK 11. The other thing you can do is you can capture a heap dump and use the memory analyzer and find duplicates. Go back to the libraries. A lot of time it will be created in libraries. You can go back to the libraries, contribute a change. You might own it, and reduce this duplication. In our case, we found a lot of duplications, but they ended up being just a few megabytes across the whole app. So we didn't find a lot of these good points to just go and make a small fix. OK, so we start to upgrade. And here's the good news. We run the app. It didn't run, but all it was, JAX-B was missing. We went to Maven Central, added the dependency for JAX-B. We learned from other services that you need to be on a new version of Log4j, but we were already in Lambda on Log4j. And we need to update Makeda from 1 point something to 2.25. We had to upgrade ByteBuddy and Lombok. But as soon as we were done, the service was running. It was fine. Like, we didn't touch the source code at all to make Lambda work. So sounds like good news. Sorry to disappoint you. We found a lot of broken tests. And most of these changes came because Makeda made a break-in change between 1 and 2. And in AWS, we care deeply about security. That's the number one thing we worry about, followed very quickly by operational excellence. So we keep up with latest security patches all the time. But since Makeda was a test dependency, we didn't worry that much about updating it. And we could have done a lot better. If we updated our dependencies in a normal fashion or regular cadence, we wouldn't have written a lot of test code with Makeda 1. We've written it with Makeda 2, and we'll be in a good place. But you learn from your mistake and you improve. So I just want to show a couple of examples. In this case, one example would be the argument matcher. We're passing in these tests null strings. And Makeda doesn't let us do that anymore. And we had to change any string to nullable of string class. These are mechanical changes, but you have to do them carefully across a very large code base. That took quite a lot of time. Here's another one that I think is interesting. I think Makeda did a really good job here. So we had an interface, and the interface declared that it's throwing an IO exception. But then we had an implementation of the interface that did not actually throw it. So in this particular implementation, there was no path, and we didn't declare the checked exception. So when you look at the test was trying to mimic what will happen if this implementation throws an exception. And Makeda said, hey, dude, this implementation cannot throw, stop. So there were actually multiple cases of this, and this was a really good lesson. We went back, and in some cases, the solution was delete the test. You cannot actually throw that exception, and nothing ever bad is going to happen. In other cases, it turned out that whoever wrote the test mocked the wrong implementation, right? So you had to go and mock the right implementation, and then we're testing something that we should be testing. So it was a good learning. We could have learned it a lot earlier. And the lesson here is if you write a lot of tests, you write a lot of code, the sooner you upgrade your dependencies, you're saving the pain later down the street. So, okay, we have a service up, and now we need to roll out. So AWS runs in 22 different regions. Lambda is a dependency a service that appears in every single region, right? Like we talked earlier, we have hundreds of thousands of customers running in Lambda. We have trillions of operations per month. We had to stop and pause and decide what are we going to do now? How do we get this such a big change out? So yeah, all our test stages are green. What do you do? So in this case, we sat down and discussed it, and the solution was, let's first roll it out to a small region. So when we choose a small region, we want somewhere that has less customers, so we can control what we call the blast radius. If something goes bad, it will happen in a small region and not in a large region, will impact less customers. But we also want a region that has enough traffic. Fortunately, with Lambda, you want to be able to try against enough variations before you move on. So the next thing is to decide how long do you want to run it, right? JDK 11 is such a big change. There's so much code that changed under the hood. How do you know that things that work today will keep working in the next 3 or 4 or 5 days or a week or a month? So you got to think about it. You got to look at what you change, and then you make that call. Once we're done in the small region, we're happy. We moved on to a larger region. Still just one more region, but now we go into somewhere that serves a lot more customers and a lot more traffic. When we're content with that, we just move with the regular rollout like we release normal stuff. Why are we doing it? There's enough unknown unknowns. Like, we don't know of any bugs, but you have to move with trepidation when you have such a large change. We talked about latent issues. We talked about limiting the blast radius. And we want to build confidence in ourselves and with our customers. If we have an outage, it's much better if it happens in one region and not across multiple regions. Obviously, we don't like outages, and we want to avoid them, and we do work very hard. But you also don't take unnecessary risks in rolling things out. So how do we do that? So we used a internal CI/CD systems. We have a public one called AWS Code Pipeline that you can use to build a similar pattern. So we have a build, and we have test stages where we test. When we run our unit tests, we run our integration tests, we run our load tests and stress tests. But that all happens in our, not in a real region. No customer traffic is going there. When we went to the first region, what we do is we have a part of that region called staging. What happens in staging is we run the new production code in a limited set of servers, and it's running against the production databases. But it's running in an area only against the test area. So there's no customer traffic coming in and out of that area. It's all fake, call it fake traffic. But what this can catch is the case of the poison pill. So we have the new code. The new code is writing something to the database that the old code cannot read. So now in the staging environment, we have old code reading from the test area, new code writing to the test area, and we make sure one can read the other. So when we deploy further, we're not creating corruption in the data. Again, obviously, we think about all these things up front, and if we have a case when we change the data, we have a deployment like that. But staging helps us catch unexpected errors or unexpected changes we didn't think exist. So once we're done with that, then we move to a stage called canary. Canary, another name for canary is fractional deployment. That means we take a small portion of our servers and deploy the new software for them. Now, what you get is you get a part of the traffic onto these servers. And when we're confident that that didn't create any issue, we have special separate monitoring for that and special tests for that. When we're confident the canary is fine, then we roll out to the rest of the region. And then when we're happy with the first region, we move to the second region. This is, by the way, our standard CI/CD practice, except in this case, we disable the automation in progressing things, and we made our own calls when we're happy, and only then push the button to move forward. So let's look at the results. The allocation rate, if you recall, we're running on the left side will be how we were on JDK 8. And on the right side, it's afterwards. So our memory allocation per invoke went significantly down at P99 and went actually nicely down on all the others. It's just much more prominent on the P99 request. GC pauses were a lot more impressive. They went down quite a lot, both the P1, or the lowest latency, and also the highest latency pause. And we think this is distributed somewhat between, if the previous slide was showing you what compact string did, this slide shows you the combination of compact strings plus the GC pauses. And then the measurable results, or what you can see as a customer. So here's the P99. It went down by 20%. And the P99, or the 4 nines, went by 33%. When I wrote this, I didn't think I'll have enough time. There's an extra, the 3 nines actually went down by 40%. So it's important to look at all the latencies and all the percentiles together and not just make a call on one number. What this actually told us is that our 3 nines was mostly impacted by GC, while our 4 nines was impacted by downstream services, and not just by GC. Given that reduction, you'd actually expect, in this case, that the 4 nines will be a bigger reduction than the 3 nines, which didn't happen in this case. So the results overall, bugs or any customer impact, there was nothing. It was a very smooth deployment. We took our time and we tested enough, and everything just went out. No surprises. The pilot deployments really built confidence in the team. Other teams in Lambda and other side services, as you can see, it's an array of microservices talking to one another. Built a lot of confidence, got excited, and now they're working on JDK 11 migration. The worldwide rollout was in August, and now I'm assuming there's a few Lambda customers in the audience. Anyone running Lambda? I see a few hands. So you now get to enjoy faster invokes. And as usual, we measure, observe, measure, improve, and do it again. Just what we do every day. So we're working now on the next round of improvements to the service. So to summarize, JDK 11 is here. It's ready for prime time. As we've seen with this service and many other services, it's actually not too hard. It didn't take a long time to make it work. It's a low-hanging fruit. To get similar type of improvements in your own code, you might spend a lot of time. So go for it. Update your dependencies. It seems like a thankless job on a day-to-day basis, but all the cool people that work on these third-party libraries are making performance improvement or fixing bugs. They're going to make your application generally, not all the time, but generally better. So just don't settle for security patches. Just keep updating your dependencies. Use CI/CD to deploy your service and save your customers and yourself a lot of time and pain. But if the changes are large and you don't have full confidence in them, don't just rely on CI/CD and push the button. Slow down, think about it, figure out what your strategy is to get things out the door. And last, another call out for our product. We're powering Amazon with Corretto. So if you're using the console, you're using S3, and now as you can see, if you're using Lambda, or if you ever bought a package on Amazon, you're already using Corretto. So give it a try, let us know what you think. And that is it. So you have about 2 minutes left. If anybody has any questions, I'll be glad to answer.
Did you have any issue regarding modularity?
No, so the application itself is not modular, and we have seen absolutely zero issues with modularity. Okay, any other questions? Thank you very much.